The answer is 3.56. So we're trying to find the surface area for the solid generated when y equals x cubed from 0 to 1 is rotated around the x-axis. And because the rotation is around the x-axis, when you select one of these frustums of the cone, the radius of the rotation basically will be the same as your function, f of x. So the formula becomes surface area equals, so our radius is going to be replaced with f of x because rotation is around the x-axis, and then we have 1, pardon me? Pardon me? 0 to 1?
Yeah.
So for this function, f prime is 3x squared. And if you square that, you get 9x to the 4. So you put that under the radical sign. Right. F of x is the function itself, which is x cubed. And then you use a u substitution, I assume, here. So x cubed dx is du over 36. And now we integrate u to the 3 halves over 3 halves. And don't forget to bring the u back in terms of x. Before plugging in the limits. And the limits were 0 to 1, correct? Once again, don't forget to plug in 0 because there's actually something non-zero coming out of that, which is 1. And if you simplify this, as Kevin suggested earlier, the answer turns out to be 3.56. Any questions about the solution before we try another example? Any questions? Okay, this next one, yes, Krista? Yes, I got the one when I plugged in 0 in for x. So if you plug in 0 for x, 9 times 0 is 0. 0 plus 1 is 1, and 1 to the 3 halves is 1. That's how I got the 1. Oh, you could do that, but usually if I have a constant right outside, what I do is I factor that constant out, and I plug the numbers, the limits of integration, to the remaining expressions. So you could have done pi times this minus pi times that. You could have done that. But if I have a constant, usually I keep it outside of everything, so I don't have to worry about it more than once. Okay, good. Any other questions? Okay. Let's take a look at this next one. Actually, just 1 second. This is the one I want. For this question, to save a little bit of time, let's just set it up. I know you're going to be able to integrate this later because there's another example I want to get to. This one is just set up the integral. We're taking f of x equals x squared. From the point 0 to root 2. And now we're going to rotate it around the y-axis. So this is the type of solid that we're getting. So what is the radius of rotation here? So your frustums are going around this way. So what is the radius there? Let's go back, look at the formula if you like. The formula was 2 pi times r of x. And r of x has usually two choices, either x or f of x, depending on what the rotation is around. Here the rotation is around the y-axis. So what is the radius of the rotation? This is just x, right? So I will go back to that formula just so I can show you one more time. Let me go back to the formula. Here it is. 2 pi r of x ds. And r of x was going to be just x. If your rotation is around the y-axis, as we've seen here, then your radius will be replaced with just the quantity x. Okay, so tell me then what the formula will look like in this case. Surface area equals what? 2 pi times the integral of what? The radius is x, square root of 1 plus f prime of x squared. And notice sometimes I put dy dx, sometimes I put f prime of x. It's really the same thing, but they both represent the derivative of the function, so don't let that confuse you, please. And for this question, I suggested we just set it up. What is dy dx here? First, just the derivative. The derivative is 2x. And when you go to this formula, you got to square the whole thing, right? So square 2x, quantity squared, so that's 4x squared. Okay, so I'm going to let you finish this one. How would you integrate this, by the way? Use substitution. I'll give you the answer. I believe it should be 13 pi over 3. Yes. Because the rotation is around the y-axis. If you look at that picture, when the rotation is around the y-axis, what is the radius of the rotation? Right, so the radius of the rotation is x. So for the surface area questions, you got to be a little bit careful. It's really still very straightforward. If the rotation is around the y-axis, you use the radius, which is x. If the rotation is around the x-axis, you use the radius, which is f of x. And finally, let's do this example, which is to show that the surface area of a sphere with radius r is 4 pi r squared. Again, another formula we've taken for granted. Today we can actually see at least one way to derive that formula. To get a sphere, what do you think I should be rotating around? Or what figure I should be rotating in the first place to end up with a sphere? Right, we can rotate it around the x-axis, but what is it that I'm rotating? Should I rotate a line? A circle, right? To get a sphere, if you want to end up with a sphere, let's start with a circle. Actually, I'm going to just take a quarter of a circle and rotate it, let's say, around the x-axis. You really have a choice as to where you want to rotate it around. It would actually be a good example if you could do it both ways. I'm going to do it one way right now. I'm going to rotate it around the x-axis. If you do the problem the other way also, you're going to really learn a little bit more about surface area. So rotate it around the x-axis, and we'll get a hemisphere. What is the equation of this curve? It's a circle, right? What is the equation of it? If the radius is r units, x squared plus y squared is equal to r squared, right? This is a circle centered at 0, 0 with a radius of r units. It doesn't matter that we're just using a quarter of the circle. It's still the same circle, so I still have to use that same equation. Okay. Since the rotation is around the x-axis, let's write down which version of the surface area formula am I going to use. The 2 pi is always there. The square root is always there. But I just need to know what to write in front of that square root sign. Should I put x or should I put f of x? F of x, right, because we're going around the x-axis. So the radius of your rotation, if you take one of those frustums, the radius of those is going to be same as the function, and the function, whatever it may be. At the moment, let me just put f of x there. And the limits will always come from the x-axis, since we always have a dx in these formulas, so it's going to be 0 to r. Let's simplify it a little bit more. In order to find dy dx, in order to plug f of x, I need to know what is y in terms of x for this circle. What is y? So since x squared plus y squared equals r squared, what is y in that equation? Would everybody agree with this? I just solved for y in the equation of a circle. Normally it's plus or minus. Why am I taking only the positive one? Because I started with a quarter of a circle, and my circle was only on the top part, right? I took that quarter of a circle, and then I rotated that around the x-axis, right? So that's why I'm only going to take the positive one, because I'm dealing with that initial graph that I had that's eventually being rotated. Okay, this is my y, or f of x. It's going to be plugged in here for f of x. So I already know what that is going to be. Okay, that's my f of x function. But how about the dy dx portion? How do you find the derivative of this equation? Start by writing to the power of 1/2. I want to hear from you guys. What is y prime? In other words, dy dx. What is it for this case? So we bring down the 1/2, right? Subtract 1 from the power. And then multiply everything by what? Remember the chain rule? By the derivative of the inside. What is the derivative of the inside here with respect to x? Negative 2x. Remember, r is just a constant. R squared might be like the number 25 or whatever number it is. So the derivative of the inside is the derivative of r squared, which is 0 with respect to x, and the derivative of x squared with respect to x, and that's the 2x portion. The 2's will cancel. And I'm going to rewrite this like follows. So what happened there? Because I had a power of negative 1/2, I brought it down as a square root. Okay, ultimately I'm going to need to know what is the square of this. When I put it into the into my integral formula, I need to square this quantity. What is the square of this from the step above? Square the top, you get this, right? Square the bottom, and what do you get then? R squared minus x squared. Before I go to the integral formula, I want to do one more simplification. We're going to need 1 plus y prime squared, right? So let's do 1 plus the quantity from above. Can you simplify this in any way? Like getting common denominators? Right, for 1 I can write r squared minus x squared over r squared minus x squared, right? And the other one is already there. Do you see a simplification now?
X squared cancel.
And plus x squared minus x squared, they cancel. So all we have is r squared divided by r squared minus x squared on the bottom. So take this and put it into the surface area formula. 2 pi times integral of f of x. What was our f of x for this question? y equals what, in other words? What was our f of x? Our f of x was, right, the square root of r squared minus x squared. That's our f of x portion. Times radical 1 plus y prime squared. But 1 plus y prime squared, we've taken a great deal of time to simplify that, and it all comes down to this. Okay. Now, this may look like a really complicated integral, but you won't believe how much it's going to simplify in the next step. As a matter of fact, I'd like to see if you guys can suggest how I could simplify this a little bit. Look at those r squared minus x squares. There's no need for u sub or anything. It's going to simplify tremendously in the next step. Everything cancels except for what? The top r squared, which is going to come out of the square root as an r. Because they're both root r squared minus x squared on the top, root r squared minus x squared on the bottom. The only thing left is just an r, because root r squared is r. You're going to integrate that with respect to which variable? X. Okay, what is the integral of r with respect to x? But rx, right? Because think of r as the number 5. The integral of phi with respect to x is 5 times x, right? So integral of r with respect to x is r times x. And the limits of integration are from 0 to r. And remember, these are from x equals 0 to x equals r. So if we plug in an r, we're going to get r squared. Plug in a 0, you get nothing. We got 2 pi r squared. What is wrong with this? The question said, show that it's 4 pi r squared. We got 2 pi r squared. Is anything wrong with this answer? No, this is half a sphere, right? To get to full one, we got to multiply this answer. So surface area for a full sphere is going to be 2 times the answer from above, which is indeed the correct answer, 4 pi r squared. There's a question, I believe. Grace, did you get the answer to that question? Okay. It's hard to believe, but Archimedes had this formula in like 300 BC. So more than 2,000 years ago, with very little math known at the time, he knew this formula. But they didn't know algebra. And they didn't know what pi was. So how could he have possibly known the formula? This is how he formulated it. He said, the surface area of a sphere is equal to 4 times the area of the biggest circle through the sphere. Think about it. The area of the biggest circle, that would be pi r squared, right? Multiplied by 4, and you have 4 pi r squared. So he didn't have algebra, he didn't have calculus, but somehow he was able to derive this using simple geometry, perhaps not so simple geometry, but you know, he's just one of the most fascinating mathematicians of all times, in my opinion. But at least with calculus, we can go back and verify what he did in more algebraic terms using the actual, what pi is and everything. Okay, in the time that we have remaining, let's go back and do a couple more examples, one on arc length once again. And this is the kind of example I was telling you about, where the integral that you end up with is very difficult, and you may have to use a graphing calculator to actually evaluate it. So let's take a look. Find the arc length of f of x equals e to the 2x from 0 to 1. And the arc length formula, based on our earlier derivation, is the integral of, again, lowercase s I'm using for arc length, capital S for surface area. Arc length is the square root of 1 plus f prime of x, or dy dx, squared, integrated with respect to x over the given x limits. So for this question, let's begin by finding the derivative. The derivative of e to the 2x is 2 times e to the 2x, right? By the chain rule, you multiply. It's like e to the u times u prime. Now we want to square that. So square the entire quantity from the step above. We'll get 4 times e to the 2x to the second power. When you have the power of a power, you should multiply the powers, and that will be e to the 4x. And putting that in to our formula, we have to integrate the square root of 1 plus 4 times e to the 4x dx, going from 0 to 1. As you can see, this is not an elementary integral. If we had an extra e to the 4x outside of the integral, perhaps we could have tried to use u substitution, but in this case, we're even told that we could use a graphing calculator to complete the problem. So I'm going to go ahead and open my calculator up. Okay, the integral symbol is under the math command. Let's see, math, FNINT, that's function integration. The function we want to integrate is 1 plus 4 times e to the 4x, 4 times e to the power of 4x. Close the parentheses. The arguments are always what you're integrating, comma the x or whatever the variable is, comma the limits of integration, in this case from 0 to 1. And there we have it, 54.6 roughly, 54.6. Okay, and the other example I'd like to take a look with you is the one I mentioned earlier today, which is the circumference of a circle. I have to say I like these examples, the kind that where it says, okay, show the volume of a sphere is this, or the surface area of a sphere, or the circumference of a circle. These kinds of problems, I think, show a real understanding of the materials covered. And if you look at your review sheet at the end of this chapter, the review sheet that I have online for you, you will see that the last problem there has like 9 parts, and each and every one is a derivation of this type. So I really want you to get a good feel for how to do these. So let's do this example. Show that the circumference of a circle with radius r is 2 pi r. Once again, a formula we've taken for granted all along. Let's try to derive it. So we're going to begin by taking a quarter of a circle with radius r and finding the arc length of this quarter of a circle. Then we can multiply the answer by 4 to find the total circumference. Once again, what is the equation of a circle centered at 0, 0 with a radius of r? It is x squared plus y squared equals r squared. And let's solve that for y. Y equals the positive square root of r squared minus x squared. Once again, I can take the positive square root because I'm dealing with the portion of the graph that is above the x-axis. Let's remember the arc length formula once again. dy dx, or same as y prime squared. So we're going to need to find y prime. As a matter of fact, we've just done that in one of our previous examples, so it will actually be very similar in that regard. Since y equals r squared minus x squared to the 1/2, y prime, by using the chain rule, will be 1/2 times r squared minus x squared to the negative 1/2 times the derivative of the inside. Rewriting that, we get this. I'm going to need to know the square of this quantity. So squaring the expression from above, we end up with this. And it's very similar to the steps that we took when we did the surface area of a sphere a few moments ago. So I also want to simplify this after I add the 1 in. And instead of 1, I can put r squared minus x squared over r squared minus x squared. And y prime squared, same as above. I'm just copying that down. And just like we did in the past with that other example, the negative x squared, positive x squared cancels, and we are left with this. Excuse me. There is no square root on the bottom. We are just left with r squared minus x squared at the bottom. Now, let's put all of that to our arc length formula, which simply says integrate the square root of 1 plus y prime squared. So just take the square root of the above and integrate it. So at this point, it looks a little bit different than that other example. Here, there's nothing to cancel, like the r squared minus x squared is canceled on the other example. Here, it's not going to cancel. Let me try to simplify this a little bit more. The square root of the top over the square root of the bottom. The square root of r squared is r. And on the bottom, we have square root of r squared minus x squared. Integration with respect to x. Remember, r is just a constant. I can take that r outside. How do I integrate 1 over square root of r squared minus x squared dx? Do we have a special formula for that? So I hope you remember the sine inverse formula. Sine inverse of x over r, limits 0 to r. And remember, these limits are set for the variable x. So we have r times sine inverse of r over r, in other words 1, minus sine inverse of 0, sine inverse of 1, in other words, at which angle is the sine function equal to 1, and the answer should be in radians. The answer is pi over 2. Sine inverse of 0 is 0, so here I have r times pi over 2. Remember, this is the arc length of quarter of a circle. So what is the circumference of a circle? 4 times the answer we got. And that is indeed giving us the formula for the circumference of a circle, 2 pi r.